Hey, welcome back. In this video, let's go through the initial calibration steps needed to make the OpenBGC firmware start doing its job. I'll assume you've got OpenBGC already running on the device and you have the release contents extracted to a directory, what we did in the previous video. From there, we'll start the OpenBGC companion app, and in this case, we cannot use the simple BGC GUI like we did previously because the calibration process just isn't compatible. Now the app is in Python, so in theory it's multi-platform, but I only tested on Linux, and an Android version is also planned soon. At the same time, I don't want to talk about what works and what doesn't work because it will become outdated fast. Okay, so just do this, client/app.py, and the app account's up. It's detected one serial port, so we'll tell it to connect to that. There are a few tabs like in simple BGC GUI with its tabs, and now it went to the status tab after a successful connection. The visualization you see here just shows the camera because we haven't calibrated the geometry properties yet. In fact, it doesn't know what the camera orientation is. It just uses the camera as a sort of symbol for the IMU sensor position. Okay, we'll tell it about like the relation between one position and there in the next few steps. So the visualization will look quite different. Okay, let's go to the calibration tab, and it gives us a list of recommended steps. So it's gonna guide us through the steps, but I'm gonna do all of this in the video just to explain little tricks here and there. The top two are already checked. The camera balance is checked because the firmware has to assume it's done, but it's up to you. I'll not go into that. You're a smart guy or girl, and the balance is really important for efficiency, but also for stability when there are accelerations acting on the gimbal, because they produce torques if there's any imbalance. Okay, next is the gyro calibration, which is automatically done on every startup. It takes 5 or 7 seconds, I think, so make sure you're not moving the gimbal. Don't touch it leave it completely static for a few seconds after power on. I'll show you later how to disable the recalibration, which will make the startup much faster, close to instant. Okay, the next three are the big ones. They're about detecting the gimbal geometry, so the physical shape. Maybe let me explain it this way. The firmware starts in a sort of virgin state with no idea about the physical layout of the arms, the joints between them, the sensors, even the camera. All it knows is it's receiving readings from those three angle sensors, the encoders, so basically one-dimensional values, and the IMU that's close to the camera at the end of the three arms, but it can be mounted in an orientation. So each sensor has an address, but we don't know where it physically is, which joint it's on, how the sensors was mounted, and what axis the joints rotate about. So we will be detecting those few things, and it's almost automatic. The firmware just needs a little bit of your help to move the arms in a specific pattern, but nothing else. And that's really good because it makes no assumptions about the joint axis. Like the specific gimbal has 90-degree angles between joints, plus or minus manufacturing errors, right? But it could be 45 degrees like some gimbals between the yaw and the roll motors. They have other, or it could be any other value. Any gimbal geometry you can throw at it, it doesn't care. It'll be able to achieve the camera orientation that it needs, the target orientations, with any combination of three joints you give it. Okay, for the record, we use the standard naming where this is called the outer joint, this is the middle joint, and this is the inner joint, right? Okay, we're in the axis tab now. Hit the start button, it's gonna be telling us instructing us what to do. So it's asking us to rotate the outer joint and to not touch the other two joints, so it can sort of isolate the joints. Alright, it's collecting samples. We're at 38 out of 64. Don't go too fast, and it's done. Move to the middle joint now. This time we have to rotate that joint and keep the inner one stable, so the one closest to the camera, But since we already got the outer joints axis, we just calibrated the outer joint, the firmware can now sort of cancel out or undo any input from the outer joint. So it doesn't matter if we move it accidentally. Okay, now the final joint, the inner joint. After this, we're done with the step. Okay. By the way, if you're gonna be doing this with the one-hand base, you will need to use a tripod. You even a pocket one like this one here will do. Just screw it in here at the bottom. Okay, let's see the visualization now, and it's showing the camera plus the arm positions, but you'll notice the joints are on the wrong sides of the camera. That's because we calibrated joints axis orientation, but not the direction from the camera. And that's because the firmware doesn't actually need this information, like it doesn't use it, so it doesn't care. But we can add it anyway for the visualization to be pretty, right? So first we notice the inner joint is on the wrong side, should be on the left, it's on the right. So we go back to the axis calibration tab and hit flip axis 2. And then the middle joint is already okay because it shows the joint behind the camera and not in front of it. But the outer joint is on the wrong side again, up instead of down. So again, flip axis 0 in that tab and we're done. So the visualization is now what it should be. Well, it's not perfect, but it does the job, right? The mapping's correct, the angles are correct, it's not too bad. Okay, so we now have the fixed part, let's say the permanent parts of the gimbal figured out. So these next two steps are about how the camera is mounted on top at the end of the gimbal arm. So because it's up to you, you can mount it any way you want. So position the camera with the lens looking at a point on the horizon. In other words, that's our zero pitch, right? Then the picture frame also needs to be lined with the horizon, so basically what you call a zero roll. And finally align the camera's forward direction with whatever the handle's forward direction is to you. So that's gonna be your zero yaw, whether you're using the two-hand base or the one-hand base. Now hit the set button, and from now on, that is what the gimbal considers the zero pitch, zero roll, and zero yaw position, or the home position. But it's completely up to you what you want to set it to, right? Where you want the frame's front direction to be. You can keep it upside down and back to front, for example. It doesn't matter, just set the home position accordingly. Okay, so now the camera has a zero position or a home position, but we didn't actually tell the firmware where the camera was looking. So it's like you set the lens to point somewhere on the horizon, but we didn't tell it where on the horizon it was looking specifically. So learning that forward direction will define the pitch versus the roll axis. So for example, you could mount the camera, you could have mounted the camera looking to the side 90 degrees from where it's now, and the home position would be the same, but roll and pitch would be switched around. So to understand our commands, whenever we're gonna tell it to pitch by this angle or roll by this angle, it's gonna need to know this extra bit of information. So how are we gonna do this? We keep the camera point exactly where it was for the home position, but we roll it to the right by about 45 degrees. Okay, that's it. Now hit the set button, and the firmware calculates the rotation that took us from the home position to this new position, and the axis of the rotation is the new forward direction. Okay, and don't worry if you didn't understand what I just said, because it doesn't matter. Just follow the indications and the firmware is gonna infer the information that it needs. Let's quickly save what we've got until now, because all the calibration results, they're stored in the RAM, in the operating memory, but not written anywhere else. So go to the connection tab and hit the right button here. and it's saved now. Now we're done with the overall gimbal's geometry or layout, and step number 6 is the motor geometry. So in a way we're done with the sensors part, and we're moving on to the actuators, so the motors. And this really refers to the motor's internal geometry, nothing that you can see physically on the outside. So it's gonna need a few parameters that it's gonna need to auto-detect, and you cannot really tell it to them unless you maybe look them up in the datasheet of the motor, specifically the number of magnet pole pairs in the rotor, and the alignment angle with the starter windings, and also the alignment with the encoder. And that last thing that even varies between one unit and another of the same model. So you don't need to know about those parameters, just let the firmware take care of it. But there's one little catch, as you'll see. Let's connect the battery power now for the first time to let the firmware actually drive the motors. So here in the status tab, you're gonna notice the voltage jumps from 0 to 16 volts, and you're gonna know that the battery is now connected and it's detected it has power. So back to the calibration tab, hit auto detect, and let's do its thing. The result's going to appear here in the console at the bottom. Okay, so it failed. And why is that? This is because it has by default a very low tolerance for error, and there was some shaking and wiggling, and it decided that the results were not exact enough for it. So it's trying to calculate the number of rotor pole pairs, and it's getting a fractional numbers, and it's need to be a integer. So it's gonna in this case the motors have 11 pole pairs each, and it will want to see a number that's between 10.9 and 11.1. So 1/10 error threshold by default. So we'll add some more room by going to the parameter editor here, finding this parameter. 10 is the default, corresponding to 0.1 pole pairs. Let's change it to 40. Set it for all three motors. Then switch to the connection tab to write those settings to present memory and read them back for the driver to update. Okay, this time it's making progress and it succeeded. By the way, another thing to try if it fails is to move the joint by hand to a different start position, like maybe 50 degrees away from what you tried first, and try it from there. It might just get a more precise result and be happy with it without any further tricks. So now we've got all those automatic steps done happily, and what comes next is the annoying part. Fortunately, it's the last major step, but it's the PIDs, and it's tedious because you have to do the work. In this case, it's manual. So you may have messed with PIDs before, but basically the PID is the firmware's way of deciding how much force to apply, how much torque to apply at each moment, so that the movement is smooth, not jerky, not too soft, not too slow, and that it doesn't overshoot or oscillate. So all those are common problems in robotic systems. So we need to tune a few parameters before it works well, and the parameters all depend on the mass distribution around the camera, and so unfortunately you'll need to redo it, recalibrate it whenever something changes in the mass distribution, the physical configuration. You might just be lucky, the default might just work, so let's see. Since there's usually some error margin where even if the values are not perfect, there might be good enough. So okay, so we're switching to the PID tab. So this is a lot of values here, The P, the I, and the D are the top three and the important ones. And we'll be fiddling with them and we'll be testing the results. To test, you can either try to start the full stabilization control loop and see how it's doing, right? Which may cause, violent shaking or unexpected movements, so there's a warning. So after you press on, like motor's on, be ready to hit the off button at any moment. If the PIDs are not correct, you might want to do like an emergency stop. Or you can also test axis by axis individually, so motor by motor, which is probably better initially, so use those buttons here under each axis. So for starters, set all the D to zeros, which is sort of a safe starting value, and maybe you don't even need to touch it again. So set this to 0, write it, this to 0, write it, and same here. You might also start with a 0i, but this value is already pretty low, so it shouldn't cause problems. So let's power on the outer motor and see how bad it is, right? And it looks like it's moving pretty stably, huh? So constant 5 degrees per second. Now in fact, let's see the status tab here. One extra feature is that you can pop out the tab and see it simultaneously with the calibration tab. So like this. Okay, by the way, we've set the speed set point to 0 now, but it doesn't mean that the motor is off, okay? So the other two motors are off, but this one's on and it's using battery, so remember to turn it off later. In fact, you can see here that the torque varying, the motor torque, as it's responding to the torque I'm applying with my hand. So you can compare also the speed set point to the actual speed that the PID is achieving. So we set it to minus 5 degrees per second, and it's staying around 4.8, so not too far. And you also want to look at the moment you stop the motor or switch direction. There's just a tiny shake there, tiny oscillation for a moment, but it's pretty good, nothing to worry about. So let's leave it at this. Okay, one thing, the I fall off parameter, I like to keep it at maybe 1/1000, so some kind of very low value. That's gonna improve the tracking a little. And the Vmax here is good. It defines how much of the total power, so the total that you can get from your current battery, motor and cabling combination, how much of that budget you want to allow the firmware to use at any time. So it limits the power to a safe value. In this case, 1/5 is more than we're ever gonna need, unless you have like a really big payload, really bulky camera, or really bad balance. So 0.2 is completely adequate and it's safer for testing. Now moving on to the second motor, seems to be good as well, even better than the first motor. Okay, now the final motor, again, it looks good. The changes in speed are in fact very sharp and no oscillation, so that's great. Okay, let's call it done. We've been lucky. It's not always going to be this easy. In fact, I'd say OpenBGC PIDs are a little more finicky than simple BGC32 original firmwares, and the implementation is apparently smarter, more forgiving at this time. So if you need to redo the PIDs here, just follow the instructions in the tab. We're basically done here, so let's save the parameters again. Okay, the next step on the list is already optional, joint limit. So you'll notice this specific gimbal has a hard stop on this inner joint axis. The other two axes have nothing, but this one has a hard stop. You shouldn't be hitting it often because it's at this extreme angle, so well designed here. But other gimbals might have limits at more shallow angles, so you can program those limit angles into the firmware in this tab to ensure that the motors aren't fighting against those limits, so they will like stop some distance from the limit, or even they could be like slamming into them at some velocity, and if you had like a very delicate camera optical system, you could maybe damage it. So it might be important. It's not important in my case, so we'll skip it. It's optional. Okay, so let's finally test it. And on, and it goes to the home position like expected. It's also stabilizing the camera in movement, and you can see the motion reflected in the status tab. Oh, and you can control which axes are in follow mode. So here only yaw following is enabled. So the camera yaw, the camera azimuth follows the frames yaw. The UI has no checkboxes for these parameters, but you can edit them directly in the parameter editor. So here follow 0.0, follow 0.1, etc. So for example, we're disabling yaw following here, but you can also enable roll following or pitch following, up to you. The other two parameters that you probably want to touch and adjust are the velocity limit and the acceleration limit. So set it to match whatever you're doing, like more cinematic slow movements or more sport mode type, whatever you want to call it. Those are in radians per second, by the way. So let me just show you how it works. Here in the status window, I'm setting some target yaw, and it takes a trajectory that respects those limits, those maxima. So if you want a slow movement, well, it's already pretty slow, right? But you can make it slower for a specially cinematic shot, or you can make it faster. So by the way, this is how you command specific target angles, or you can also set a target speed. I can click on the speed bar here to send a new set point, new target, or I can just hover over the bar and then hit send separately, or just type in a value and then hit send. So let's try 8 degrees per second, and we can also track how well it's keeping that speed, how close to it's maintaining. So let's set 6 degrees per second the other direction now, and I'll click send every second or two. One final cool feature in this app is the control pass-through, so let me quickly show it. Let's say I want to control the camera pitch with the mouse pointer Y coordinate, and I want to control the yaw with the X axis here. Minimum and maximum like 200 degrees. And I want the scale, let's do 100. And we're going to start the motors, okay. So the sign is wrong. Now it's okay. It's following the pointer basically, but always respecting max acceleration and velocity that we had set previously. Okay, one more option is tab. Let me fast forward a little. We can also use the laptop's built-in sensors. So most laptops, they have, an IMU like mobile phones do. So we'll try the gyros, and we'll make the gyros control the gimbal speed this time, not the angle. And by the way, this is Linux only, guaranteed not to work on Windows or Mac at this time, because it's quite platform specific. The ratio there is 58, which is just the ratio of radians to degrees, like the 180 divided by pi. Okay, and here we've both pitch and yaw, and it's still tracking correctly. Okay, so that's it for the video. I hope it's a useful rundown of the setup. Perhaps it'll allow you to decide if you want to try OpenBGC at all, and maybe whether you want to try adding your own gimbal model, because I realize the PilotFly H2 is over 10 years old now, so probably rare now. On the flip side, it can be found really cheap, and it still has the high-end feel. I don't think it's obsolete by any stretch. I don't see that these devices have advanced much since then, except if you talk about maybe the tiny full integrated gimbals, not that the do-it-yourself friendly ones. So I got 2 units of this for pennies basically, and mechanically they were perfect. Oh, and here's the remote, which also works with OpenBGC, but it takes a while to connect since it's Bluetooth, and it's also a little bit, the potentiometers are worn out. Here it is paired and working. You'll need to use the left button there, the menu button, for motors on and motors off.